Okay, so in our last lessons, we looked at how to do a polar form of a rectangular coordinate and how to do polar forms of rectangular equations. What we're going to look at today is how to use the polar coordinates to represent complex numbers. Now let's review complex numbers. Complex numbers were numbers that had a real part and an imaginary part. And if we actually look at what is called the complex plane, it is represented with the real numbers along the x-axis and the imaginary numbers on the y-axis. So if I wanted to graph the complex number 2 plus 3i, that means I'm going 2 in the real world plus 3 in the imaginary world, and this would be the point 2 plus 3i. Well, where would z2 be? 3 minus 2i. So 3 into the real, down 2 into the imaginary. Now C says to take z1 plus z2. So that would be 2 plus 3i plus 3 minus 2i. And let's simplify that. Well, the real parts would be a 5. The imaginary parts would give me a 1i. So 5 and then 1i. 5 plus I. Now I'm going to add one extra on here that I should have put in to begin with. And that would be, what if we just had negative 4i? Well, that would be no real parts and then minus 4 imaginary. So no reals, so we'd start at 0 on the real axis and go down 4. That would be negative 4i. Now the next thing I'm going to look at is something called the modulus. The modulus of a complex number is its distance from the origin. So let's say I have some complex number a plus bi. That means I'd go this way, some a distance, I'm just making it up, and we go up some distance b. This would be the point a plus bi. Well, we want to know the distance that is from the origin. This is what we want to know. Hey, isn't that like our r? And don't we know the relationship here? A squared plus b squared equals r squared. So to find that distance, we'd take the square root of a squared plus b squared. So complex numbers we tend to write with a z, and the modulus is written with these absolute value bars. And let's think about why we write it as absolute value bars. Your absolute value is the distance from 0. Distance from the origin. Distance from 0. Means the same thing. So this is actually asking us to find the modulus, find the distance to the origin. So here's our little formula. We're going to do the square root of a squared plus b squared. So that's going to be the square root of 3 squared plus 4 squared. So that would be 9 plus 16, square root of 25, which is 5. Let's try the next one. A squared plus b squared. So a is 8. This time b is a negative 5. But what's going to happen when I square it? What's going to become positive 25? And when I add those together, I get 89, and I don't think that's a perfect square, so I'm just going to leave it like it is. Now let's look at how we can represent complex numbers in polar form. So there's a few things I want us to remember. Okay, so let's redraw that picture. Okay, so this would be our A, this would be our B, this is the point A plus BI, this is our R. We could also think about this angle as being theta. Now there's a few things I want you to think about and remember from last unit. So one thing is we already know that R r squared would equal a squared plus b squared. So we could do it. R is the square root of a squared plus b squared. We also already knew that tangent of theta equals b over a. But we also know that x equals r cosine theta and y equals r sine theta. But in this instance, the x that would get us to that point is actually our distance this way. It's our a. And this is our vertical distance. That would actually be b. So let's see how I can rewrite this. A is actually r cosine theta. And b is actually r sine theta times I. Now, to write this in the normal way we write it, a lot of times we'll see this r and the r, and we can factor out the r. We can undistribute it. Also, when I undistribute the r, I'll have sine theta times I. It's a lot of times better to write the I in front of sine, just so people know it's not with the angle, it's being multiplied by sine. So let's see how we would do this. The first thing I would ask you to do is do a quick sketch of where this would be. 2 plus 2i. So 2 plus 2i would be over here somewhere. Good to know. The next thing I would do is find r. Well, r is equal to the square root of a squared plus b squared. So the square root of 2 squared plus 2 squared. That's going to be the square root of 8, which is 2 square root of 2. The next thing you're going to do is find theta. To find theta, we're going to use tangent equals b over a. And it does, opposite over adjacent. And so the b value is 2, and the a is 2. So I've got tangent equals 1. Well, to find the angle, we are going to do the arctan of 1. And you could do this in your calculator if you wanted to. So let me go back to the calculator. If I do shift tan, that gives me arctan of 1, and it tells me pi over 4. Now I need to make sure that is the correct answer, and pi over 4 would be in the first quadrant, so that is the correct angle. Sometimes it gives me an angle in the first quadrant, and I really wanted a different one, so we have to play with it, and we'll see that happen. So remember we started with 2 plus 2i. Well, that written in polar form would be r times cosine of the angle plus I sine of the angle. Let's try another one. Negative 3 square root of 3 and negative 3. So if I looked at where that is, that would be negative and negative. That'd be down here somewhere. So I need to remember it's down here somewhere. So first step, let's find r. R equals the square root of a squared plus b squared. R equals the square root of negative 3 square root of 3 squared plus negative 3 squared. And you could do that in your calculator if you wanted to. That'd be square root of 27 plus 9, which is 36. And you get r is 6. The next thing we're going to do is find our angle. Tangent theta equals b over a. And you can literally just go from here. Arctan of negative 3 divided by negative 3 square root of 3. I mean, I'm typing it in just like I saw it. And it's giving me pi over 6. Now, my problem with that is pi over 6 is over here. But what I really want is the angle that goes this way. And what it's doing is it's actually going pi over 6 past that x-axis. So that's like having pi plus pi over 6. And that gives me the angle 7 pi over 6. Does that make sense that that would be 7 pi over 6? If we looked at our unit circle, it would. So this in polar form, we start with our r, and then it's cosine of the angle plus I sine of the angle. And if you go into future classes, some college classes, instead of writing this all out, they write it as cis, 7 pi over 6. That stands for cosine I sine. I just wanted to show you that. Now, what if we were given a polar and we're trying to convert to complex numbers? In other words, we're trying to take that and go back to a plus bi. What's actually easier than you think. So we have this number on the outside of the parentheses. So what I'm going to do is, first off, let me find the stuff on the inside, and then we're going to distribute. So it's square root of 2, cosine of negative pi over 3. You can go either to your unit circle, or you can type in cosine of negative pi over 3. And it gives me 1/2. Plus I, and then sine of negative pi over 3 is negative square root of 3 over 2. Well, square root of 2 is being multiplied to all of that, so I'm going to distribute. So square root of 2 times 1/2 would be square root of 2 over 2. Then I have the I, but let's see here. So this would be negative square root of 2 times the square root of 3. That gives me square root of 6 over 2, but it's negative. And I'm going to put the I at the end so it looks like that. And that's it for that. The next thing we're going to look at is multiplication and division. And there's 2 rules for that. The first rule says if I'm multiplying 2 complex numbers, I am going to multiply their R values and then add their angles. To divide, I'm going to divide their R values and subtract their angles. Easy enough. So to multiply this complex number times this complex number, I'm going to take the 2 times the 5. Let me write it out. 2 times 5. And then inside, I'm going to take pi over 4, the angle here, plus pi over 3. So that would be plus I sine of pi over 4 plus pi over 3. So I got a 10. Now, feel free to use the calculator to figure this out, or you could come off to the side and see if you remember your fractions. To add fractions, we need a common denominator, so multiply this one by 3 and this one by 4, and I get 3 pi over 12 plus 4 pi over 12. I've got 7 pi over 12. But yes, you could put that in the calculator and it would find it for you, pi over 4 plus pi over 3. Now let's divide. So to divide 2 complex numbers, we divide their R values. And then we're going to take their angles and subtract. So this time I'm going to subtract. So this was 3 pi over 12 minus 4 pi over 12. So that would give me cosine of negative 1 pi over 12, so negative pi over 12, as my new angle.